Good morning, Professor. Today I'll be presenting my internship report on impedance matching network design for our rectangle. My field supervisor is Dr. Ari and academic advisor is Heru Putra. Okay, I would like to elaborate on the internship objective. First is to understand the proposed rectangle technology and topology, since we're not just looking at one different type of topology of rectangle, we're looking at multiple. We also focus on reproducing these existing technology before we develop our own. And the last one is after developing our own, we also have to develop matching impedance between how you said, the new topology that we design. And finally, our objective is to improve our skills in CST Studio Suite and Keysight ADS. Okay, and this is the place where I was interning in. I was interning in Brin, Jalan Sukarong at Dago. This is me over here. This is the professor, Pa Ari, and this is my co-worker, also from Telkom. Okay, so let's talk about why we even picked this topic or why we were given this topic. Before, our professor was working on a certain paper. This paper mainly focused on development of a airflow sensor using a batteryless airflow sensor using the CSRR technology. As you can see from the graph that the sensor works really good around 30 to 60 kilograms with varying frequency. And yeah, so he wants us to make it to be able to be functional at cold places. And I propose that what if we use a rectangle technology to how you say make it um how you say to give it power so that it can work in cold environments. Okay, so this is initially how the rectangle works. A rectangle has an antenna. It has a it has an input filter, an impedance matching network, a rectified circuit, and a storage element, and then the load over here. One of my coworkers focus on these aspect of the rectangle design, and the other focuses on these aspect. So I won't be elaborating on the antenna and filter uh, and uh, and the rectifier. I'll be elaborating on my part. It is the matching network. Now, why do we need a matching impedance or like matching network? So the thing about radio wave is that as it becomes bigger in megahertz, gigahertz, and terahertz, the wavelength becomes shorter, right? And sometimes these wavelengths can bounce if the impedance is not same. The bouncing of these create like standing waves. The bouncing of the incident waves create like a standing wave. At low power, it doesn't really, like affect the component. It's just, uh, gives power loss, but at a higher power, it can actually damage or even melt the component. Because at standing wave, you can see over here that the frequent, uh, the amplitude of it is higher than the incident reflective wave. And yeah, this can lead to high currents or high voltage, which can destroy the component. Okay, so regarding about the matching impedance, we know by international standard that antenna should be 50 ohms. So I didn't really focus on how to get that. I just typed it as the ideal 50 ohm. But the resistance load is complex because a rectangle design often have a lot of complex components like uh, sorry, not complex, but like lump elements and also like complex element like Schottky diodes, which like it's non-linear. As you can see, we have two. This is the right one. This is the left one. The left one is for a half wave rectifier. We use a Schottky diode that's called SMS 7621. This is different than the paper. We use this one over here because this is the one that we want to manufacture. Oh, sorry, we want to make the rectangle with. And from the result, as you can see over here, we got like 30 ohms and a real ohm of 30 and imaginary ohm of minus 713. And this one over here, how do I say, is a full wave rectifier, as you can see from the design. Sorry, I think so. I placed a wrong picture. It shouldn't be like this. This two shouldn't exist. It should just be the entire thing. But yeah, this is the result of the full wave rectifier. Uh, as you can see, the real impedance is 6 ohm and the imaginary one is minus 327 ohms. Okay, now you might be wondering how did I design uh half the matching impedance? Well, there's this feature in ADS called a um, Smith chart. So basically, I just input 50 ohms over here, and I input the complex ohm over here, and I basically have to position it to the center. Okay, and this over here is an example of me using lump elements to how you say mm, to to get like a lower S11 and S21 parameter. As you can see, the S11 parameter is really good. That means that at this frequency, that there's no reflect, almost no reflection at all. And this can be, and as you can see, when I simulated and we got a same result, that is we got a minus 37 dB and a very almost zero high side dB at S21 at the desired frequency. That means that there's almost no reflection at all. This is using a lumped element. But then again, when I showed this to my professor, he said that like lump element have parasitic values, and that can change the result drastically. So he want us to use a microstrip technology. So and that's what I did. I tried to use a microstrip line, but it was really difficult. And as you can see over here, it also requires a resistance. But as you can see that compared to this one of minus 37, the S1 parameter is actually really high. But as you can see, the S21 parameter is minus 18. There's some loss in the power transfer. I think so. It's mainly because of the resistance. As you know, like the energy, some of the energy is dissipated in heat. And we showed that to the professor, and the professor, like was not really impressed by it, and they want us to what if we utilize full phase of the electromagnetic wave and harvest both of the phases. And that's why we moved to a full wave rectifier. The full wave rectifier, we of course initially designed it using a lumped element, but as you can see, that th- from the Smith chart alone, the design should work perfectly. But when we simulated, it didn't work. I have no idea why. I tried. I think so is mainly because the circuitry of a full wave rectifier is a bit too complex, and there are some additional feature that I didn't really take consideration that I didn't know of. Yeah, that's like the full wave rectifier, but as you can see, it's really bad. This basically means that there's a full reflection, 98% reflection. I think so. Yeah, and this is the full wave rectifier using how do I say, a microstrip line. I try using microstrip line without using the lumped element, but because the how you say the capacitance is the impedance, the load is more towards capacitive. It's really hard. So I use another capacitive to push it away from this point over here all the way to the middle of here. And as good as oh, it's not as good as the previous one, but the result is much better than the previous one, as you can see. I think so. This is mainly because due to the parasitic value, right? Since this one only has one lumped element and this one has two lumped elements. But yeah, the conclusion is that we successfully reproduce and analyze the RF energy harvesting rectangular system at 2.5, especially, I mean, as in like we successfully developed using the half wave rectifier. We also designed and validated impedance matching network for the Schottky diode rectifier using the lump element and microstrip transmission line. We also, and I mean, the matching process demonstrated the importance of accurately extracting the rectifier complex impedance and considering parasitic effects and practical implementation. And finally, improve practical understanding of CST Studio Suite, Keysight ADS, Smith chart analysis, RF simulation, and impedance matching. If you have any question, feel free to ask. And yeah, that's all from me. Thank you so much.